Okay, so welcome to the 34th lecture on control of active and reactive powers. I hope it was the last lecture was clear. I'll just quickly recap that in the last lecture we discussed about this basic generation control loops and how the right hand side of the loop, which is AVR loop, and the left hand side loop, which is LFC loop, how do they behave in a simple layman's terms, how their logic is there. I hope it is clear to everyone. Also, we saw this primary ALFC loop or primary load frequency control loop in a detailed way, that how exactly this diagram works and how the each point goes up and down to open the control valves of the uh, of which will allow more steam and water to flow to turbine. So is there any query in this lectures? Okay, if no queries, then let us move forward and see this governor. So basically, if you will see that in this particular diagram, the main uh, item is the speed governor. I hope you have seen the or you have understood the concept that this speed governor, actually the way it reacts based on the wall movement, that actually controls the frequency of the power plant and eventually the speed of the power plant. Right, so this speed governor is the main key feature of load frequency control, and if you are able to understand this speed governor, then everything is very clear. So you see here that the speed governor plays an important role. I hope this is clear, because rest all is very mechanical. Only the speed governor is the thing which gives a feedback. If the valve opens, that means the steam, more steam will pass to the turbine, and the more steam will pass to the turbine, that means the speed of the turbine will increase. That will increase the frequency, and the speed increases, that means speed governor uh, pushes the B point down. So here is this B point which is pushed down. If these two balls, if the speed increases, then these two balls will move away, and if they move away, they will push the B point down, and as soon as the B point moves down, then everything eventually stabilizes at an equilibrium point where the valve remains open at a particular position. Right, so now the speed governor, let us see what exactly, or this is all mechanical, but how we represent it in electrical sense, let us see that. So this speed governor, if you will see here in the first diagram, the speed governor is having input of steam or water which is entering to the turbine via valve or gate, and this valve gate opening is controlled by governor. So as soon as the speed of the turbine changes, the governor action opens this valve and stabilizes the speed at a particular required speed. And you also see that the torque TM is the mechanical torque and TE is the electrical torque. So you can see here that the TM and TE are moving in opposite direction. It is from the simple concept that turbine is rotating in a particular direction. That is the direction of the torque in which mechanical torque is applied, and electrical load is acting as a reverse force on the turbine, and that is actually giving as an electrical torque. Eventually generator will have some mechanical power input, it will give some electrical power output, and that will satisfy the load PL. right? So to represent this in a simple sense, you can say that the torque, mechanical torque minus the electrical torque is the net torque, which is equal to 1 by 2 hs, where h is the inertia constant of the machine and s is the Laplace operator, and this delta omega r is the rotor speed. So to get the speed of the machine, this is the main control action what we have to do, right? So this is I'm actually showing you in I'm not showing you everything in detail, but here in the broad sense you got the idea that this governor from the previous lecture, if you change this means the speed changes, the governor actions decides how much valve to be opened, so that the speed comes back to the normal state. And this here, why I am saying this h here, h is because of this inertia, because generally if you have seen any practical generators or not, but if you see the practical real-time generators in power plants, they are of huge sizes, and huge sizes means it will be generally to the size of 3 to 4 floor building, that big it is in the diameter of that rotor or of that generator. So you can imagine it is so heavy that even if the mechanical torque is removed, it will still keep on rotating because of its own inertia. So that plays a very big role in deciding the speed. So both weight is strict. So let's say if the weight, obviously the weight is high, so to start you need lot of mechanical torque to start rotating the machine, and you to stop the reverse, to stop this machine, or to rotor to stop, you again need a lot of effort and lot of reverse power to stop the rotation of this machine. So therefore inertia plays a very big role here, right? Any queries? Okay, one query you can ask me here, that we are studying a course of power system. So obviously if you see here, if we focus on torque, this becomes really difficult to visualize and solve, to study or to do analysis on our power system. If we focus on torque sense, it will be difficult. So let's convert this torque expressions into the power expressions, right? So let us do that. There is a small derivation. So here, how does generator response to a load change? So this is the way we decide, we convert this the torque expressions into the power sense. So basically power is equal to omega r into t. Omega r is the rotor speed and t is the torque, right? So this is the conventional formula. Now for small change in the load, let's assume a small change in the load. So there will be some initial power P naught, and due to that change there will be some change in the generation power, that is delta P. And if that difference is there, then in the torque also initially there is some torque, and it will change the some torque change will be there. And similarly you can say this for the rotor speed, that there is initial omega naught speed is there, and then there will be change if of delta omega r, right? So let's talk in terms of small deviations. So when we talk in terms of small deviations, then if you put this equations P, T and omega r in the first equation here, then you can see that P naught plus delta P is equal to T naught plus delta T into omega naught plus delta omega r. And here just focus on the delta P part, or the perturbed value part, because this constant parts are P naught, T naught and omega naught, we can ignore that. and then delta p, if you see just the derivative part, so that will give you this delta p equal to omega naught delta t plus t naught delta omega r. Right, so you can just multiply and do these calculations. Just focus on the perturbed values. You can equate this equation and focus on the perturbed values. Now here we to get the torque, this expression what we saw in the previous slide, here we saw that mechanical torque minus the electrical torque was equal to the speed with inertia multiplication. But so basically it is mechanical minus electrical. So this expression is valid for both mechanical and electrical power and torques. So just write the same expression with for mechanical and the same expression for the electrical and subtract it. So basically delta Pm minus delta Pe will give you omega naught delta Tm minus delta Te plus Tm naught minus Te naught into delta omega r. Right, so this will be the equation for the mechanical and electrical terms. Now here omega naught you can assume 1 per unit, assume that the nominal speed is 1 per unit, and initially at the stable point, because here we are talking again about the perturbed situations, at the stable point the mechanical torque will be equal to the electrical torque. And if we put these values here, this part will go away, this will be 0, and here omega naught becomes 1. So eventually you will see that the mechanical power minus the electrical power is actually equal to the mechanical torque minus electrical torque. This is for the perturbed values. When it is stable, there is no issue. Only during the disturbances you can correlate that the difference in mechanical and electrical torque is equal to the difference in the mechanical power minus the electrical power. Right. So now what we can do is, in the previous slide we saw this diagram. Here you can actually substitute the same thing in this diagram. Here instead of torque you can mention mechanical power minus the electrical power. See here it is plus minus electrical power should be 1 multiplied by 1 by 2h s. Here I am writing m just to give a common term for it, ms, and s is the Laplace operator. This gives the equation or the expression for the speed or change of speed in the rotor in per units. Right, so again I am not going into very fine details here, but I hope you are able to connect it. Or is there any issue in the connection from where we are getting these expressions? Okay, good. So we are basically converting all the terms into the power terms here. So basically if you want to, if you see a change in speed or rotor speed, how much mechanical change you have to put so that the equivalent rotor speed you will get, that you can get from this equation or this control blocks. Now there is one more important point here, as we have discussed previously in the we discussed about brownout. So brownout is because of the voltage change, and the concept here was that as the voltage changes, the load value changes and the behavior changes, because of which further catastrophic actions happens, and which eventually lead to the brownout. Now similarly even the loads, obviously they depend on voltages, but apart from voltage they also depend on frequency. So basically whatever device you will take, either you take your motor devices, either your air conditioner, refrigerator, fans, tube lights, or your laptops, or any other device you take, if the frequency changes, the value or the power consumption of these devices also change, specifically motor devices, because in the motor the eddy current and hysteresis losses value changes, and even as they changes, obviously the performance of the motor changes, and most of the devices are motor devices, though they start behaving differently and their power consumption value is different. So therefore, obviously, if there is a load change, let's assume if there is a load change is here, delta P, then obviously as soon as the load changes, there will be the change in the rotor speed, because it's logical, right? If the load changes or load increases, then the speed reduces, or if the load decreases, the speed increases. Now how much you have to control this delta PM, that you can decide based on that. So let's say if the load has increased, then the speed has reduced, so then you have to increase the speed, so you have to increase the delta PM, or you have to increase the mechanical power, right? Now, but the problem here is that obviously the load has changed, the speed has changed, but the load change has further changed. So the concept is like this. I'll tell you in the next slide. So basically, load also changes based on frequency. What does I mean here? I was telling this here, that whatever is the electrical power required, a change in electrical power has been done because of the change in the load. There will be two portions of the load. One portion which is a non-frequency sensitive load change. So basically, if the load changes, that means let's say 1 megawatt of load has changed, then that 1 megawatt will, there might be some portion of that load which does not depend on frequency. So obviously it will not change. It will change, means let's say you have switched on or switched off a particular device. Let's say a heavy motor you have switched off or switched on. So basically the load change will be in such a way that some portion which is not dependent on frequency, those load will change differently, and the loads which are dependent on frequency, their change will be in a different sense. So it is called as frequency sensitive load change. So here this D is the load damping constant, which actually tells you that, for example, I can quickly say, let's say for example right now the load was 100 megawatt, right? And then let's assume 10 megawatt of load reduction has taken place, right? Now as soon as the 10 megawatt of load has reduced, then the frequency will increase. Let's assume it goes beyond 50 and it goes to 51 hertz. But as soon as frequency goes to 51 hertz, then the load, the other loads which are actually connected, their load consumption will actually increase because the frequency has increased. And as soon as the load consumption has increased on the other appliances, those load will now consume more power than what they are consuming initially. So now let's say they were consuming, let's say 90 megawatt, now they will be consuming 95 megawatt. So eventually the load drop is of 10 megawatt, but because of the increase in the frequency, the remaining loads are now consuming more power. And because of that, eventually the net load reduction is just 5 megawatt. So basically, if let's say 10 megawatt of reduction has taken place, then as soon as the 10 megawatt of reduction has taken place, then obviously this will include some load which is actually minus 10 megawatt, which is actually reduced, or sorry, let me just quickly tell it this way. So here we can ignore. So actually minus 10 megawatt of loss has taken place of load, and then as soon as this loss has taken place, the frequency increases, and as soon as the frequency increases, the rest of the load increases their consumption. So let's say they increased their consumption by 5 megawatt. So eventually the delta P is actually minus 5 megawatt. You get my point? Similar to voltage, the logic of voltage what we gave, the same logic is valid here also. So the load changes based on the change in the frequency, and this therefore for every load there is some damping constant. They naturally come arrive at a equilibrium point, or they can arrive at equilibrium after some oscillations. So this change is actually known as is represented by load damping constant, which is, you can say it, a percentage change in load for 1% change in frequency. So 1% change in frequency will lead to 1% change in the load, or whatever is the percent. So generally this is 1 or 2%. So most of the loads in India, most of the residential loads, or if you see in the bulk load also, all the loads are mostly 1 to 2% range. So 1 to 2% means, or let's say if I say 2%, what do I mean by 2% here is that, let's say if the load was 100 megawatt, so if, and at 50 hertz, right? Now if the frequency has changed by 1%, 1% of 5 hertz means, let's say 1% of 5 hertz is 0.5, right? So let's say it has increased by 0.5. So let's assume it is increased by 0.5 hertz. So this 100 megawatt load will change by 2%. So 2% of 100 is what? 2 megawatt. So this load will change to 102 megawatt at 50.5 hertz. So you see how the load varies based on change in frequency, and this is typically 1 to 2% in every system. So you can see here, although the load has reduced, but obviously because of the frequency increase, the load will further rise. The rest of the loads which are actually connected, they will start consuming more. So you do not need to give the mechanical power of the complete value what you have lost. You have to give the mechanical power only to the equilibrium consumption value, not to the complete load loss. Obviously again it will further increase the frequency. So basically here, when load has lost, so let's say 10 megawatt of load was lost, so you do not need to reduce the mechanical power by 10 megawatt. You have to reduce it by just by 5 megawatt, because the rest 5 is being settled by the frequency increase. Right? So here the idea here is, now you can see here, or if let's say if I draw this diagram, if let's say f is here and time is here. So what actually is happening is, let's say the frequency at this point is 50. Let's say this is 50. Now what is happening is, let's say if the load has reduced or load reduction has taken place, then what will happen, the speed governor, what it is going to do is, the frequency is rising as the load has reduced, and it will eventually settle at a particular value, at a new frequency value. So this is going to be a new frequency, let's say 51 hertz, right? But this speed governor, or this governor action, will not bring the frequency back to 50. It is just going to settle the frequency at a particular value. So as I told you here, as the load has reduced, therefore the frequency will increase, and as the frequency is increasing, then other loads which are actually connected, they will start consuming more power, and because of which the net load reduction is not the actual load which has reduced. You got the point. The net load is different and the actual load is different, what we lost. And eventually this delta PM has to satisfy that the speed reaches to this value and settles down at that value. It does not go on increasing further, because if you pump or reduce more load, then what will happen, then further the frequency will increase, because the load is also increasing because of the increase in the frequency. Right? Any confusion here? So if we are talking till here, we are not talking that what happens when, how to bring this frequency back to 50 hertz. This we are going to see later. This is the later part. We are just focusing on that the frequency should stabilize at a value. And how does it stabilize? As soon as the frequency, the load has reduced, the frequency has increased, and the frequency has increased, that means the other loads which are connected, they have started consuming more power, and because of which the mechanical power what you have to reduce, you do not have to reduce to the value of the actual load lost, but you have to reduce to the value which stabilizes the frequency and the net load that you have to satisfy. Okay, so I hope you got the concept. Let us see it further, and you can see here that we can make it an equivalent diagram is basically delta Pm minus delta PL multiplied by Ms plus D. M is the inertia and D is the damping coefficient of the load. This gives the actual change in rotor speed of the machine. Now let us quickly solve this numerical here. I request everyone to quickly read this problem along with me so that you get the idea of it. So basically a small system consists of 4 identical generators. 4 generators are there, generating units are there having 500 MVA each, right? So basically there are 4 generators of 500 MVA capacity and they are feeding a load of 1020 megawatts, right? So whatever is the combination, maybe each generator was generating some small value and the sum of all those 4 generators are satisfying the load of 1020 megawatt. And here the inertia constant H is basically, let's say, 5. So 5 means that the inertia of the machine is calculated in terms of 5, and this is for each this is on the 500 MVA base because it's also in per unit, so it's on the base of 500 MVA. And also the load has a damping coefficient that load varies by 1.5% for a change of 1% frequency change, right? And when there is a sudden now the question is, when there is a sudden drop in load by 20 megawatt, determine the system block diagram with constants H, D expressed on 2000 MVA base, right? So now the question is, we have to actually calculate so here we have delta PL, this is in minus, here we have delta PM, this is in plus, so this is the block diagram. Here it is 1 by M S plus D, and this is delta omega R, right? So we have to calculate the value of M and D on 2000 MVA base. So now M is what? M is basically 1 by 2, or rather not 1 by, it is just 2H, wait. So M is 2 times of H, right? Now 2 into H is what? 5, and this is on 500 MVA base. Now you have to convert this on 2000 MVA base. So how will we do this? We'll just 500 divided by 2000. So this value is at 500, just divided by 2000, it will give you the ratio. And now this is for one machine, but here you see the important is because this is the single block diagram what we have to draw. So or the question is system block diagram what we have to draw. So system block diagram means the complete system has how many generators? 4 identical generators. So you have to multiply the inertia, or the inertia will be 4 times the value what we are getting here, right? So system block diagram we have to draw. Think about this. So here if you'll see this, so it will be 500 into 4 is 2000, it will cancel out, it will be value will be 10. Clear to everyone? Now what will be the value of D? So D is basically 1.5%, right? And this is also at the MVA base of this is also at the 500 sorry so basically here also you have to convert it to 2000 MVA base. So basically what is the actual load after that sudden drop in load by 20 megawatt? The actual load is 1000 megawatt. So basically if you want to calculate the net load, again I'm using the word net load, not the actual load, although actual load is 1000 megawatt, but the net load will be something else. It depends on the frequency. So here the actual load is now 1000 megawatt, and if I want to calculate the variation in the load, I'll calculate based on the actual load, and then 1.5% of that will be the net load. And this 1000 is divided by 2000 to basically make it in the terms of 2000 MVA base. So this will give the value of 0.75%. Right? So basically I have converted all the parameters into 2000 MVA base. Right? M and D both are in per units. So this is the system block diagram. Here the value of M is 10 and the value of D is 0.75. Right? Now, is there any query? Shall I move ahead? Okay, there is a second part of this question. Now, the